So welcome back once again, and in the last lecture we have studied refraction through plane surfaces, and today we talk about refraction in spherical surfaces and lenses. The laws of refraction, the same laws will be applied, and we will consider infinitesimal part of the surface to be rather planar. Okay, and we'll also consider that the aperture of this surface, which is separating the rarer medium from the denser medium that we have taken, mu1 is less than mu2, and mu1 and mu2 are with respect to air, which is taken the standard. Then under the condition like this diagram goes, okay, we have the small angle approximation for the aperture is being too small as compared to u, v and r. Okay, then you can see that this is the principal axis for the system, and a ray of light starts from the object O and goes through the pole and through because it will be undeflected. Of course, there may be a small reflection back into the first medium, and well, the ray of light which is coming from O to N, this is, you can see that this is the angle I, and it is refracted in the denser medium through a smaller angle R, which intersects the principal axis and the first ray under consideration at the point I. So point I is an image of the object O, and this is the pole of the system, and this point is taken as N. When we drop a perpendicular from N onto the principal axis, is actually because it has been exaggerated, but actually it drops. We'll consider that it drops at the point N. Okay, with that approximation in mind, with the small angle approximation taken as valid, this is from O to M is taken as U, and from M to I it is taken as V, and the R value is from here to the point C, this is center of curvature. Now, if you look at the different angles, then angle NOM, okay, this angle, the tangent of the angle will be equal to NM divided by OM. Okay, bear that in mind that this point and this point are one same point. Tangent of the other angle, NCM, tangent of this angle, this will be equal to NM divided by CM. And similarly, the tangent of the angle NIM, this is again NM upon IM. Okay. Now let's see for triangle NOC. Okay, this is a triangle that we have, NOC. Angle I is the exterior angle. Okay, so therefore I is equal to NOM plus NCM. Okay, which is from that approximation NM upon OM plus Mn upon Cm. Okay, and similarly we can see that this angle R plus this angle they make, and they are equal to this angle. Okay, so we can write that angle R is equal to angle NCM minus angle NIM, which I can write therefore from this approximation NM upon CM minus N upon IM. Okay, now Snell's law defined like this: sin I upon sin R is equal to mu2 upon mu1. So I can write it as mu1 sin of I is equal to mu2 sin of R. And in the small angle approximation, sin I is equal to I and sin R is taken as equal to R. So we obtain, for small angles, we obtain this relation. Okay. And substituting, we'll obtain in the due course of time the equation which defines the refraction of the system. Okay. So mu1 I is equal to mu2 R. Okay. So if I substitute the values of I and R, then I get mu1 Mn upon Om plus mu1 Mn upon Mc is equal to mu2 Mn upon Mc minus mu2 Mn upon Mi. Now Mn are common, so I divide throughout by Mn, so I get mu1 into 1 upon Om plus mu1 into 1 upon Mc is equal to mu2 into 1 upon Mc minus mu2 upon 1 upon Mi. Segregating those, okay, so mu1 upon Om plus mu2, I bring from here mu2 upon Mi is equal to, because Mc and Mc are common, so mu2 minus mu1 upon Mc. Okay. Now in this relation, if I apply the Cartesian sign convention, okay, that Om is equal to minus u, Om is equal to minus u, and Mi is equal to V in the same direction, and Mc is equal to R in the same direction as the incident ray. So I get mu2 upon V, this one, plus mu1 upon u is equal to mu2 minus mu1 upon R. This formula holds for any spherical curved surface interface. Whether mu2 is greater than mu1 or mu2 is smaller than mu1, whether the surface is convex or the surface is concave. So in continuation we take a double convex lens. Okay, convex on this side and convex on this side. It falls at the point N1 on the face ABC, which is a convex face, and then there is a concave face over here, but this is also convex like that at N2. Part of it has been shown with the diagram that from O to N1 at the face ABC, the ray is falling, and we have I and R like that here, and we get an image I1, and of course this is R1. This side is the rarer medium, and this side the denser medium mu2. Upon when it is coming out of the other face, then at N2 the ray is coming like this, and basically what I1 is a virtual image. Okay, this face is ADC, this is R2, and this side is mu2 and this side is mu1, and the final image is obtained at the point I. Now we have the equation mu2 upon V minus mu1 upon u, this which I call the equation number 0. Okay, if I apply it to the interface ABC, this interface which has been shown over here, has been drawn over here with all the drawings that you have at our disposal, this will turn out to be equal to mu1 upon OB plus mu2 upon bi1, okay, is equal to mu2 minus mu1 upon bc1 from the formula that we have applied. We call it number 1. Applying to the other face with values of mu1 and mu2 taken over here, so I get it minus mu2 upon di1 plus, because this image is a virtual image, plus mu1 upon di is equal to mu2 minus mu1 upon dc2. Okay, this I call equation number 2. Now, for a thin lens, bi1 and di1, they are almost equal because this is supposed to be very thin. Okay, so when we add these two equations, then this part and this part, they cancel out. So what I get is mu1 upon OB plus mu1 upon DI is equal to mu2 plus mu1 upon into 1 upon BC1 plus 1 upon DC2. Okay. If the object is at infinity, then OB becomes equal to infinity and this term becomes equal to 0. And DI becomes equal to what we call F, which is defined as the focus. Okay. So I'll get mu1 upon F is equal to mu2 minus mu1 into 1 upon BC1 plus 1 upon DC2. Okay. The image is formed at the focus. In fact, there are two foci. This one on this side and the other on the other side, that we are going to discuss shortly. So BC1 is taken as plus R1 in this case, and DC2 is taken as minus R2. And when we substitute these, then we get the formula that we call the lens maker's formula. 1 upon F is equal to mu2 1 minus 1 upon into 1 upon R1 minus 1 upon R2, where mu2 1 is equal to mu2 upon mu1. So this is the famous lens maker's formula. So you give any focal length, you describe the things, you give the refractive index of one medium with respect to the other medium, and then they make the values. And this formula is also true for the double concave lens or convexo-concave lens or concavo-convex lens or plano this lens, other lens. In this case, in the double convex lens, R1 is negative and R2 is positive and F is negative. So combining those equations before, we obtain a formula like this. Okay, and you can see that in this formula, mu1, 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 so that will all be eliminated, dividing it throughout by mu1, and then what we find is something very interesting, that for the thin lens, if B and D are close to the optical center, this is the optical center, okay, because it is a thin lens, then B and D are very close to it, and when I substitute that BO is equal to minus U, BO is equal to minus U because the ray is coming like this and this is in the opposite direction, and DI is equal to plus V, okay, using the sign convention, this Cartesian sign convention, then we obtain the famous formula 1 upon V minus 1 upon U is equal to 1 upon F. Okay, this is applicable to all sets of lens designs that we have. We can have a convex plane, we can have double convex, okay, like this convexo-concave, etc., etc. These kind of things are there for which the same formula will be applicable. Of course, we have to just consider as to what is the things according to the sign convention. So we have learned in today's lecture how formation of an image is there due to convex lens or double convex lens, and we have explained with the help of these diagrams as to how these things are obtained, this and this. I wind up over here, and in the next lecture I'll talk about the various lenses and how these formulae are used over there, and again I will tell you about what is known as the power of a lens. Okay, that is in diopters. We'll talk about that in the next lecture. Thank you very much. Thank you.